So we're going to start with a little physics experiment. Here we have a piece of glass, my own reflection, and a hammer. And here it comes. So this was kind of fun. But the question is, I suppose, is how does this relate to sea ice? And the relations to sea ice is that, interestingly enough, ice and glass break in a very similar way. And actually ice and rocks and the Earth's crust, they all break in a similar manner, something we would describe as with what's called fracture mechanics. So fracture mechanics, a fracture is a crack. As we see here, a very nice, long, virtually straight crack from the point of impact and outwards. And it's this kind of cracking which is typical of the way sea ice breaks. And here is a slightly different scale. So this is a satellite image. It's about 1,000 kilometers from top to bottom. And here we see the ice in the Beaufort Sea. And what happens is that there's a storm coming in. It comes in from the left. It goes actually here below. And the wind, what happens is the wind breaks the ice and then pushes it out of the Beaufort Sea. So it's breaking and pushing, and you can see these very large, largely straight cracks again. So this is one point which I find very fascinating actually about sea ice and the way it breaks, is that sea ice is a solid, so it will only move when it's broken. And you can see here, this is not land, this is ice as well. But this ice has not been broken yet by the storm, and therefore it stays put. It doesn't move. In order to move ice, in order to move sea ice, you first have to break it, and then it will flow. Another interesting thing about cracks in the ice is what we call leads. A lead is a crack which has started to open up a bit. And to understand why they're important, we should maybe first go to what happens when the ice is not broken. So when the ice is not broken, it acts as an insulator. And ice actually is an excellent insulator. In the Arctic, we have the Arctic Ocean, which is cold, about a -2 degrees, but still a lot warmer than the atmosphere. And the atmosphere can easily go down to -40. And the reason you can have this huge contrast in temperatures is the insulation effect of ice. Now what happens when the ice breaks and starts to open up is that atmosphere and ocean come into direct contact with each other. And that means that the ocean loses a lot of heat in a very small location. You start to form ice, you lose heat into the atmosphere, you warm it up, you lose moisture into the atmosphere, you change a lot of things about what happens in the boundary layer, in the layer of air just above the ice and the layer of ocean just beneath it. So these are very important and very interesting processes, and it's something that you can only really look at when you know how the ice breaks. So what do we want to do to capture these effects? Well, what we do is that we are creating a computer model of ice, a numerical model, something that fits in with climate models. And this numerical model of ours is quite unique. It's quite special, and we like it a lot. What it does is, not only does it simulate the way the ice moves and grows and melts and so on, but it simulates the way it cracks. It simulates the way it breaks. So to demonstrate this, I have a model simulation here. Here we have the gray patches are land, and the blue is undisturbed ice that is not broken. And the color shows how broken or how damaged the ice is. And when we start the simulation, everything is unbroken, and then we slowly turn on the wind. And you can see it starts damaging, it starts cracking, and quite quickly we have these straight lines, cracks, just like what we saw in the video first, of the glass breaking. And before long, the entire Arctic is full of cracks, the process gets a lot more complicated, a lot more interesting. But this is what happens, and this is what is special for our model. And with this model, we can do a lot of cool things, a lot of interesting stuff. One of them is also to look at the heat being lost from the ocean into the atmosphere. So here we have, again, the Beaufort Sea. And the color is now the amount of heat the ocean loses into the atmosphere. So where it's blue, the ice is thick, it's solid, and it's insulating well. And where it's sort of yellowish, there are leads, the ice is cracked and opened up, and the heat flows through. And this figure also shows that how the ice moves when it breaks. So down here, it's not breaking a lot, and it's not moving a lot. But up here, in the Beaufort Sea again, it's moving around a lot where it breaks. So to sum up, it all starts when the ice breaks. It all starts with a crack. You break it, and then you can move it. You break it, and then you can open up. You form these leads with the ice, with the ocean and the atmosphere connect. And when you break it up, when you open it up in one place, you squeeze it together somewhere else. And that's where you form also ridges, which are these mountains of ice where the ice is piling up, being squeezed together. But it all goes back to the crack. It all goes back to how the ice breaks. And this is the part that we are interested in.